Hello team, in this lesson we'll explore modern pattern matching in Java 21, including enhancements to switch, instance of, and record deconstruction. I'll walk you through practical examples that show how these features make your code more expressive, safer, and easier to read. So here's what we'll be covering in this lesson. First, we'll briefly revisit the traditional switch statement in Java and discuss its limitations that existed before pattern matching was introduced. From there, we'll trace the evolution of pattern matching, starting with the instance of enhancements and moving toward its integration into the switch construct. Then, we'll dive into how modern switch works with type patterns. I'll show you how to match by type, handle null safely, and use guard conditions with the when keyword. After that, we'll explore more advanced capabilities like record patterns and how we can use them to deconstruct objects directly inside switch cases. You'll also see how nested patterns work and how they allow us to match deeply structured data more naturally. We'll then talk about exhaustiveness and completeness in pattern matching, particularly how sealed types and enums help ensure our code covers all cases. I'll also explain the new support for comma-separated patterns and where they can simplify your logic. Along the way, we'll look at common mistakes, such as unreachable cases and incompatible patterns, and how the compiler now gives us better validation and smarter error messages. And of course, I'll walk you through a practical demo showing dynamic type-based dispatch using switch and patterns. Finally, we'll wrap up with a discussion on when and why to use pattern matching in switch, and I'll share my own perspective on when it fits well, and when a more object-oriented approach might be a better choice. Let's begin! Now, I'll proceed by sharing my screen and presenting the source code examples I've prepared for this lesson. I'm sure it will be easier for you to learn through practical examples. All source code is available in the attachments to this lesson. I encourage you to pull the code from the repository and try the examples on your own computer. And of course, if anything is unclear during the explanation or after the lesson, feel free to post your questions below the video. I'll be happy to answer them. Alright team, let's begin by revisiting something familiar, the traditional switch statement in Java. For many years, switch has been a core part of control flow in the language. It allowed us to handle different execution paths based on discrete values, such as primitive types like int, or reference types like string and enum. And for basic use cases, it worked just fine. Let's take a look at a classic example. Suppose we have an integer variable, and we want to print a message depending on its value. We might write something like this. At a glance, this is straightforward. If code is 1, we print 1. If it's 2, we print 2. Otherwise, we fall into the default case. Simple, concise, and readable. However, there are several limitations that become apparent as soon as we try to expand beyond basic types. First, traditional switch did not support null values. In fact, passing null would result in a null pointer exception. That's not ideal when we're working with potentially nullable references. Second, the traditional switch was limited to a handful of types, primitives, string, and enum. That meant we couldn't use it to operate on general object types or any kind of structured logic. And finally, perhaps most importantly, there was no support for patterns. That is, we couldn't perform type checks or extract values directly inside the switch block. If we wanted that level of expressiveness, we had to fall back on verbose if-else blocks using instanceof and manual casting. So while traditional switch got the job done, it was fairly rigid. But as we'll soon see, modern Java has evolved this concept dramatically, bringing pattern matching into the picture and giving switch a powerful new life. Let's explore how. Let's now take a moment to trace the evolution of pattern matching in Java, a journey that began with a relatively modest but impactful enhancement to the instance of operator. Prior to Java 16, performing a type check followed by casting was one of the most repetitive and error-prone patterns in Java code. You have probably seen this dozens of times. if object instance of string, then cast object to string type. Here, we first check the type and then immediately cast to that same type, a redundancy the compiler could surely help us avoid. And so, starting with Java 16, pattern matching came to the instance of operator. This small change had a big impact. Now, using pattern matching, we can write far more concise and expressive code. For example, if object instance of string, then let's work with this variable as with string type without additional casting. Notice how elegant that is. If O is indeed a string, then the compiler automatically casts it to a new variable s, scoped to that if block. There is no more boilerplate casting, and no chance of class cast exception. We can even go a step further and combine this with conditions. Let's say we only want to act on even integers. This is a prime example of how pattern matching doesn't just reduce code. It improves readability and safety. The compiler understands the structure of what you're doing, and it supports you with precise type narrowing. So, in essence, Java began its pattern matching journey here, with instanceof introducing structural and type-aware logic in a clean, declarative way. And from here, the concept continued to grow, evolving into what we now see in the much more powerful and expressive switch pattern matching in Java 21, and that's exactly what we'll explore next. Now that we've seen how pattern matching began with instanceof, let's take a step further into one of the most powerful evolutions in modern Java: pattern matching inside switch statements and expressions. Traditionally, the switch construct was limited. It could only work with a small set of types: int, string, enum, and it required exact matches. But starting in Java 21, switch has become smarter, more flexible, and far more expressive thanks to pattern matching support. So what does that mean in practice? It means we can now match by type inside a switch. Let's consider this example. Here, if the object is a string, it's automatically cast to s for use within that case block. If it's an integer, it's bound to I. There's no need for manual casting, and the compiler ensures type safety. But the improvements don't stop there. One of the long-standing flaws of the traditional switch was that it couldn't handle null values. Passing null would simply throw a null pointer exception. That changes now. The modern switch can match null explicitly. This makes your code more defensive, more robust, and, let's be honest, just more intuitive. Another powerful addition is what we call a when guard. This lets us add conditions to our patterns. So not only can we say this is an integer, but also this is a positive integer. If the pattern matches and the condition is satisfied, the case executes. If not, Java keeps looking. This opens up a whole new dimension of expressiveness in control flow. All of these improvements make switch far more capable, no longer limited to primitive values or rigid comparisons. Instead, it becomes a rich declarative mechanism that lets us inspect both the type and the structure of our data, and even reason about values through custom conditions. This is no longer the switch you learned as a beginner. This is a modern, pattern-aware, intelligent construct that brings Java one step closer to functional expressiveness, while still keeping its strong static typing and reliability. And by the way, team, pay attention to the syntax. You can use the arrow syntax in switch starting from Java 14 instead of old syntax with colons. It works in both expressions and statements, and it's also a key part of modernizing Java's control flow. As we continue exploring pattern matching in modern Java, we now come to a particularly elegant feature introduced in Java 21 version: record patterns. By the way, you can find separate lesson about records in this course if you want to refresh your knowledge on that topic. Now, if you recall, Java's record classes are a concise way to define immutable data carriers. They're ideal for modeling structured data, things like coordinates, user profiles, or shapes, without all the boilerplate. But pattern matching takes them to the next level by allowing us to deconstruct records directly within a switch statement, extracting their components in a clear and expressive way. Let's consider a simple record called box, which contains a label and a shape. The shape itself might be another record. perhaps a circle or a rectangle. Now, instead of manually unpacking these objects with getters and nested if statements, pattern matching allows us to describe exactly what we're looking for and extract the pieces we need right in the switch. In this example, you can see how it works. What's happening here is quite remarkable. In a single line, we're saying, if the box contains a circle, give me the label and the radius. Or, if it's a rectangle, give me the width and height. There are no calls to label or shape, no manual instance of checks. It's all handled by the pattern. And this brings us to nested patterns, which are exactly what they sound like. Patterns inside patterns. In our case, we're not just matching the outer box, we're going further and matching on the type and structure of the shape inside it. This nesting is powerful because it lets us express deeply structured logic in a way that's both concise and type-safe. From a readability standpoint, this is a major win. Anyone looking at your switch can immediately understand the structure of the data you're working with and what values you're extracting. From a maintainability perspective, you're letting the compiler do more of the work, checking patterns, verifying exhaustiveness, and handling nulls where appropriate. So with record patterns and nesting, Java gives us a tool set that begins to resemble pattern matching in functional languages, but with the familiarity and structure that Java developers expect. It's a perfect example of how modern Java is evolving. Powerful features without sacrificing clarity or safety. It's time to look at a concept that makes Switch not only more expressive, but also more reliable, and that is exhaustiveness. Now, what do we mean by that? In traditional Switch constructs, we often had to rely on a default case to ensure all possible values were handled. But that was mostly a safety net. The compiler didn't really know if you had covered all possible options, especially when working with object hierarchies. This changed with the introduction of sealed types in Java. By the way, there is a lesson about sealed classes in the course. Please check it if you missed it. Sealed types, such as sealed interfaces and sealed classes, allow you to explicitly declare which subclasses are permitted. For example, suppose we define a sealed interface shape that permits only two implementations, circle and rectangle. That creates a closed type hierarchy, and it opens the door for the compiler to understand the full range of possibilities at compile time. So, when we write a switch on a sealed type, like this, the compiler knows that these are the only possible cases. There's no need for a default and no fear of an unhandled branch. This is what we call an exhaustive switch, a switch expression that covers all valid cases based on the known structure of the type. And because the compiler enforces this completeness, if we forget to handle one of the permitted subclasses, it won't compile, which is exactly the kind of safety we want in production code. Let me just comment one line and you will see compilation error. Java compiler would force me to add a default case. And it's worth noting that this concept of exhaustiveness isn't limited to sealed types alone. Java has supported exhaustive switch statements over enum types as well. When you cover all enum constants explicitly, the compiler treats the switch as complete, allowing you to omit the default case. So whether you're working with a sealed hierarchy or a well-defined enum, the switch in modern Java can now serve as a fully verified, compile-time checked decision structure, giving you both safety and clarity in your code. This makes pattern matching even more powerful when paired with sealed types, because it allows for expressive and safe logic over well-defined domains. Think of financial transaction types, message protocols, or domain models where the number of possible cases is controlled. Sealed hierarchies and exhaustive pattern switches make these systems not just cleaner but provably correct at compile time. So as we've seen, modern switch is no longer just about choosing between a few primitive values. It has become a robust, type-aware, and compiler-assisted decision mechanism. When combined with features like pattern matching, record deconstruction, and sealed types, It brings a new level of elegance and reliability to Java's control flow. Now let us turn our attention to a subtle but powerful enhancement introduced in modern Java: comma-separated patterns in switch statements. This capability allows us to consolidate multiple constant labels, such as null and default, into a single, unified case. While it might not sound revolutionary at first, its impact becomes clear in the context of cleaner and more expressive branching logic. To demonstrate this, let's consider the multi-label pattern method. Here we use a switch statement to inspect the runtime type of an object. If the object is a string, we bind it to the variable s and print a message indicating that it's a piece of text. If it's an integer, we do something similar and print that it's a number. But the real highlight comes in the final case. You'll notice that we write case null default. This syntax means that both the null input and any other unmatched types will be routed through this case. Without this syntax, we would need two separate cases, one for null and one for default, even though both may result in the same logic. With this enhancement, we avoid duplication and make our intent clearer. If the value is null or simply unrecognized, we want to treat it as a default scenario. So as you write or refactor modern Java code, take advantage of comma-separated patterns in your switch. They make your logic cleaner, more robust, and easier to understand. As with any powerful new feature, pattern matching in switch brings not only flexibility, but also a greater need for precision. The good news is that Java's compiler has grown significantly smarter to help us avoid the kinds of subtle bugs that could sneak into more dynamic languages. But to take full advantage of pattern matching safely, we also need to understand where the common pitfalls lie, and how the compiler protects us from them. One common mistake developers run into is the use of incompatible patterns within the same switch label. It might seem tempting to combine different patterns into a single case, like this, but this will immediately result in a compile time error. Why? Because these types, string and integer, don't share a common usable structure that would allow them to be grouped under one case label. The compiler expects all patterns in a multi-label case to be structurally compatible. They must share a common shape or context that the runtime can dispatch uniformly. In this case, there is no such commonality, and so the compiler steps in to protect you from what would be confusing or ambiguous logic. Another classic pitfall comes from dominance of patterns, sometimes called pattern shadowing. Let's say you start your switch like this. Here, you might assume you're handling general objects first and then strings separately. But in fact, string is a subtype of object, so the object or case already matches everything, including all strings. As a result, the case string s will never be reached, and the compiler will flag this as unreachable code. This is an example of pattern dominance, where a broader pattern effectively swallows any more specific patterns listed afterward. Thankfully, the Java compiler is now smart enough to detect these issues at compile time. It checks for reachability, pattern compatibility, and exhaustiveness, all to ensure that your pattern matching logic is both correct and maintainable. So while pattern matching greatly enhances what switch can do, it also raises the bar for how precise and intentional your code needs to be. The compiler is your ally here, not just enforcing rules, but guiding you towards more robust, error-free design. And that's exactly the kind of safety modern Java aims to deliver. As we come to the conclusion of our exploration of pattern matching in switch, it's important to step back and reflect not only on how this feature works, but also when and why we should consider using it. Pattern matching in switch brings a significant leap forward in terms of expressiveness and clarity. It allows us to write code that dynamically adapts to the type and structure of data at runtime, without relying on clunky chains of instanceof checks or unsafe typecasts. The compiler helps us enforce exhaustiveness and type safety, while the syntax itself has become much more concise and readable. It's particularly useful when we deal with heterogeneous data. When a method accepts an object or a sealed hierarchy, and we want to clearly dispatch logic based on the actual type and structure. That being said, let me share with you a personal and professional reflection. Despite the power of the modern switch, I personally tend to avoid using it as a core mechanism for branching logic in my application architecture. Why? Because whenever I find myself writing a switch, it usually signals to me that this logic is likely to change. New types might be added, new cases might appear. This opens the door to violating the open-closed principle, one of the cornerstones of clean object-oriented design. That principle tells us that code should be open for extension but closed for modification. But switch forces you to modify existing code every time a new variant arrives. In other words, the switch is brittle. It has to be touched each time something new is introduced. Instead, I often prefer to lean on polymorphism. I define a common interface or abstract class and let each concrete implementation encapsulate its own behavior. That way, when new behavior is needed, I simply create a new subclass, without altering any existing code. It's scalable, modular, and respectful of encapsulation. But, and this is key, as professional Java developers, we must not be dogmatic. We need to be fluent in all the tools the language offers, including switch and pattern matching. There are places where it makes perfect sense, for example, in utility methods, in quick data processing logic, or when working with external types or sealed hierarchies that you don't own. In those cases, pattern matching gives us the power to write code that is both expressive and safe. So even if you, like me, prefer polymorphic designs most of the time, understanding how to use pattern matching in switch makes you a more versatile and effective Java developer. Because in the end, it's not about favoring one approach blindly, it's about knowing which tool to use for which job. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We reviewed the limitations of traditional switch statements and how Java evolved to overcome them. You learned how pattern matching works in switch expressions, including matching by type and handling null safely. We explored the use of when guards to add conditional logic to cases. Together, we examined how to deconstruct record objects and apply nested pattern matching. We discussed how Java ensures exhaustiveness in switch when working with sealed types and enums. I showed you common mistakes, such as unreachable patterns, and how the compiler helps detect them. Finally, we wrapped up with practical advice on when to use pattern matching in real-world scenarios. That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.